All right, we are going to talk about optimization today. Let me turn it off before I get in trouble again. We're going to talk about optimization today. Optimization is, again, when I start to think about calculus actually getting pretty interesting instead of just being a class where you take derivatives and you just do the power rule all day, every day. Today is day 15. This is SL2. This is 5.8. And we're doing optimization. Now in class we did a little exercise. We started off with a 8-inch square. And then we cut squares from all four corners that were the same size. Then we kind of made a box out of it and we did it like this. Okay. Now, optimization is about optimizing whatever it is that you have. Sometimes that's optimizing materials or optimizing volumes or optimizing lengths or optimizing areas. And optimizing is a super important skill for any business. The optimization of how you cook and prepare the foods is important for restaurants. Optimization is something that companies, especially big companies, spend an insane amount of money on. To talk about a few things that have been optimized in that way, without getting too boring. When I was a kid and I used to, everybody had sodas and we'd drink sodas and whatever. Every single soda, every single drink came in 12-ounce can, just a classic 12-ounce can, which of course is classic. But nowadays, you see tons of other kinds of cans. You see little 10-ounce cans. You see skinny, tall ones. I know there's a lot of energy drinks and my wife drinks Celsius, which is in this little skinny drink. And the skinny, tall drink is probably 5% because it's different, because it looks different, but it's probably 95% because mathematically it is more cost effective to do a skinny tall can. Maybe it maximizes their use of the material they use to make the can. Maybe it improves the efficiency of the label printing on the can. Maybe it improves the efficiency of the shipping of the can. But if I'm running Celsius energy drink or whatever it is, and you say, hey, if we do a 10-ounce can instead of a 12-ounce can, I can save you 20 cents on every can, and I'm about to sell 20 million cans. That's a pretty big deal. So optimization is a huge deal. Another good, reference is, you guys are just a bit too young probably to be purchasing toilet paper and paper towels and things like that. But you see commercials where it's a toilet paper roll and they're we've got ultra rolls, and it's it's 4 rolls wrapped up onto one roll, and oh man, I love my new Charmin Mega Roll, right? And it's just ridiculous. And again, that's not because they're trying to be cool. Nobody thinks that a Mega Roll is cool. They just are saving money. The mathematician said, hey, what if we just wrap up 4 times as much and sell it for the same price? And then what if we change it? It's all just optimization. So here's what we're doing. We have this box. We started off with a square. We cut different corners from it. We made different boxes. And we also talked about the dimensions of the box and the volume of the box. Okay. My box, I cut 3 inches from each corner, which gave it a 3-inch height. And it started off with 8 inches. And so when I took 3 and 3, I had 2 left in the middle. And so my rectangular prism was 2 inches by 2 inches by 3 inches, and 2 times 2 times 3 is equal to 12. So I had a 12-inch cube volume. Now, we all had the same exact amount of material, an 8-inch square. When you made your cut, did you make the exact same volume as me? No. Was your volume bigger or smaller than mine? Bigger?
Bigger.
What do you mean probably? Do some math real quick and multiply three numbers together and you'll be alright. So a couple people have made bigger volume. So what if we were gonna go apply for a college, or maybe we were gonna go apply at Google, and there was 100 people out in the lobby, and they said, here's a piece of paper, whoever walks in with the biggest volume gets the job, right? On one hand, it's a little bit silly, but on the other hand, you all have the same piece of paper, and so whoever can find that maximum volume wins. Now, it can be a little bit difficult to just find the maximum volume, okay? You guys that said you were bigger than mine, do you have the volume calculated? What volume did you have? 32. 32? What'd you have?
16.
16 you said? Did you get it sorted out or?
Yeah, I'm pretty sure that's 8 because it's 2 times 2 times 2, so 8.
It shouldn't be 2 times 2 times 2.
So I did
How much did you cut from the corners?
2 inches. Oh, wait, no, that
2
would be 2 times 2 times.
So it would be 2 tall,
Yeah.
but then when you took away 2 and 2, you took away 4 from 8. So it should be 2 times 4 times 4.
Okay, alright.
So that should be 32 as well. Is that what you did? 2 inches? Okay, cool. How many did you cut?
1.
1. Okay, so we tried cutting 2 inches away, cutting 1 inch away, cutting 3 inches away. So what does it seem like? Well, I cut too much and was too small. You guys cut too little and were too small. And she maybe cut Goldilocks and was right in the middle. And so now it's like, well, dang, I can't just pick a bigger number or a smaller number. There's some value in the middle that is more difficult, okay? If we thought about this and we graphed this, here's 1 inch, here's 2 inch, here's 3 inch, and then here's our volume. This can be 10, 20, 30. What we have so far is 116, which is right here, 232, which is right here, and 312, which is right here. So what do these shapes, these points kind of lead you to believe so far? Any shapes from math that remind you of this kind of thing? Quadratic, parabola. Now, it does look kind of like this, but 32 is our biggest so far, but is it our guaranteed biggest possible? If we were in the room with 100 other people trying to apply to Google, there would probably be some other people that came up, in this area. They'd probably, and it would probably fill out like this, but maybe there's some dots that are a little higher. Maybe there's some dots that are way higher, right? We haven't figured out yet. So, where would we look on this graph to find the biggest volume? It's an easy answer. Where would you find the maximum volume? At the top, at the maximum. We would look up here for the maximum. So, if we were able to graph a function that represented our data, we could maybe use our calculator to second calculate the maximum value, sure. But this question has been built and engineered so that we can actually find this maximum with no calculator needed whatsoever. So, instead, since we're not going to use a calculator, we still want to think about there's some sort of quadratic here. Our maximum value is up here somewhere. So what is our strategy going to be for attacking and finding that maximum value? What is true about the graph right here? The slope is 0, which is great. Now let's write that in terms of calculus. Another word for slope is gradient, and if the gradient equals 0, in calculus, that means the what equals 0? The derivative. We love it. Okay, so here we are. If we find the derivative of a function, that's going to tell us what the slope is, or the gradient. And if we set that gradient equal to 0, that will be where all of our stationary points are, where our maximums are, where our minimums are, and we're going to look for maximums. So here's our goal. Come up with a little equation, then take its derivative, set it equal to 0, and find out what that maximum value is. So here is how optimization works. Step 1, make a function. I'm gonna leave 3 bullet points, and then we're gonna go down to step 2. Because we've already come up with this part of the step. Once we have the function, we're gonna want to take derivative, and after we take the derivative, we want to take the derivative equal, or set the derivative equal to 0. And then lastly, determine if that is a max or a minimum. This is all things that we know how to do. Okay, so the good news about optimization is that theoretically, absolutely nothing new that we're learning today. Okay? Taking a derivative, like we've said a couple times, it's going to be easier than some of the crazy derivatives we've done before because the difficulty is a whole experience. Setting the derivative equal to 0 should be pretty easy. Most of the time you're going to be working with quadratics, where you know how to solve a quadratic, whether it's the quadratic formula or factoring. Sometimes it might even just be a straight up linear function that you have. Rarely it might be a cubic, but if it is a cubic, then you can probably use GCF to take an x out or something like that. And then determine if it's a max or minimum. Now, what is the easiest? Let's go back here. Make a function, okay? So, here's our goal. We need to make a function so that we can take its derivative. And in order to do that, because we are working with real life shapes and we are working with volume and maximizing volume, what is one of the places that we want to start? Formulas are basically where we need to look because we're working with trying to maximize a formula. So volume, and what is the volume of a rectangular prism? Especially one that we've talked about has a square base. Normally it would be length, width, height, but ours has a square base. So one of these would be doubled. And then let's use letters that we would use typically in a derivatives problem. So let's say x squared times y. We feel good about that? Again, we cannot move on until we're super comfortable with that. We're feeling good? Okay. Awesome. Now, here is our problem. Make a function and take the derivative, but when we look at this, can we take the derivative of this? It kind of looks like maybe we could take the derivative of it, but if we try to take the derivative of it, okay, here's my try. We need to take the derivative of v. A lot of times we're going to use the dv dx or the dy dx kind of format. Normally we put dy dx because we're taking the derivative of x. So down here is whatever we're going to take the derivative of. Normally it's an x, sometimes it's a theta. But our problem is that we have multiple variables still in our equation. So we already know that this is going to be a bust because we have 2 variables going on. And if we're looking at these 2 variables, we could do, product rule of 2x times y plus x squared and then the derivative of y. But this, still, what are we doing with this, right? Set it equal to 0. We have x's and y's, and we don't know. Okay, so this, it isn't really working too well, okay? That is our first real kind of like issue here with making the function, okay? We need one variable. Only can use one variable. Now, this is pretty much something that is never gonna start the problem with one variable, okay? That's what, honestly, that's where all the difficulty comes from, is from step number 1. Because taking the derivative 0, and determining the maximum, those are actually easy steps. All the difficulty is coming from making a function. So you can only use one variable. The way that you can do that is mostly use two formulas, or pretty much and, but use substitution. So a very common thing is to use two formulas. For our question, we don't really have two formulas. We just have the one. Now, we just have the one. What we need to do is go back here, work with this, but we need to find some way to rewrite one of these letters. Now, our box, which we made, which looks like this, right? Let's label everything that we have on our box. So, any numbers or letters that you know about our box, where do they go? What do you got? Where is the X? Where is the Y?
X is like the line.
Is it on the outsides?
No.
Is it on the little squares?
It's in the square.
Okay, it's in the square. Is it play tic-tac-toe? Top left, top middle, top right. Where's the X at?
Be in all.
Would it be in all of them? So we have X squared. Here's where the X would be in this middle box here. This is our middle square. It would be X and X. And then Y is whatever number that we cut out, like right here. And there only ends up being one Y because those two Y's fold together and make one Y. So here's our little equation. What other number do we know in terms of our shape? Because we didn't have an unlimited box. We were constricted in one way. We were constricted by the number 8. We know that our whole box at the start was 8. Okay, so let's do this. Let's put those all together. We need to find a way to rewrite either X or Y so that it's all in one letter. Now, because X is being squared, I'm probably going to leave that one alone. And I'm probably going to try to figure out Y. Right? So if I'm trying to figure out Y in terms of X, I actually can make some sort of equation because X and Y's are connected. Okay? The total value of 8 is equal to what?
X plus Y.
Not quite X plus Y, but you're very close. X
Plus 2.
plus 2Y, because there's a Y on the right and a Y on the left. So now, we kind of have our two formulas, which was written up in our little thing there. Now we have our volume formula, and we have our, I guess you could call it like width of the original square formula. And once we have this, solve one for a letter and substitute it into the other. Again, I'm probably gonna leave the x alone because it's squared. It's probably easier if I swap out the y, which is not being squared. And so let's go here and solve for this y. I'm gonna subtract x to the other side. Subtract x to the other side, 8 minus x equals 2y. Divide both sides by 2, and I'm getting y equals 4 minus 1/2 x. Is that right? Because I divided 8 by 2 and I divided x by 2. I think we're good. So now I'm going to do a replacement into that y. B equals x squared 4 minus 1/2 x. And now everything is in one variable. Now, if I was going to take dv dx, obviously, because there's no more y's, which is great. I have made a formula with one variable. I'm ready to go. This should be the easy part. We should be able to finish this question 2 minutes, 3 minutes, and be done. Take a derivative, set it equal to 0. Now you're pretty much done. Check if it's a maximum or a minimum. Now, how are we going to take the derivative of this? Doesn't look like chain rule to me. It looks like product rule because we have part A times part B. I don't really see a piece inside of another piece, which would be chain rule. You know, something like this would make me think chain rule because that is something, you know, non-trivial to another power. But actually, in order to even ignore the product rule, what if we just distribute that x squared really quick? That won't be very hard. And then we'll just have a polynomial. We can just do power rule, and it'll be even easier. So let's just distribute this x squared. V is equal to 4x squared minus 1/2 x cubed. You guys go with that? Let's go derivative time equal to 0. The derivative of the volume in respect to x is equal to 8x minus 3/2 x squared. Because I put the 3 in front, which is why I ended up on top of the 1/2. Everybody cool with that so far? Equal to 0. And now let's solve this quadratic for 0. We can use the quadratic formula. We can use factoring. Complete the square probably sucks. How do you guys want to attack this one? This is just algebra 2, solving a quadratic. What are we going for? Can we factor this? Or do we have to use the quadratic formula? I think we're gonna go GCF, right? There's no C term. We've only got those 2 terms. Everybody has an X. So let's just take out an X and then set our 2 things. So I'm gonna just GCF out an X. When I take away the X, I'm gonna have 8 minus 3/2 X. Okay. And I'm gonna get 2 answers now. One answer is gonna be x equals 0. The other answer is gonna come from the other side, which I'm gonna have to solve this little algebra 1. 3/2 x. Multiply everything by 2, 16 equals 3x. Divide both sides by 3. X equals 16/3. All right. So here's what we've just found. We set the derivative. equal to 0. We found x equals 0 and x equals 16/3. Those are, because of the way derivatives work, places that we have stationary points. Those are places where our slope is 0. And those are interesting because they might be where we are having maximums or where we are having minimums. So let's think about these two numbers that we got here. First of all, how does it look if x equals 0? If I draw one of these same shapes and my middle box has an x value of 0, how does my box end up looking? It doesn't really exist, right? The 0 represents when I started and I cut my squares and I cut all the way to the point where I cut out exactly, a quarter of the box. And I just cut the box into 4 corners and all the pieces fell to the ground and there's no more box. So what do you think 0 represents? This is a volume minimum, which is kind of a duh thing. That's why it's probably not clicking in right when I ask the question, because it's like, oh yeah, I mean, if your volume is 0, then that's probably the minimum, right? Imagine the Google guys asked, whoever comes in here with the smallest box is gonna win. Or the Google girls, perhaps, could be anybody. Now we've got this one, x equals 16/3. And so, what do we think 16/3 is? Probably the maximum. We've already found the minimum. Now, how can we be sure it's the maximum? Well, we know for a fact that it is a stationary point. There's no arguing that. Now, if we check the second derivative and see if the second derivative is positive or negative, then we'll be sure whether it's concave up or concave down. So let's take just a second looking at the second derivative. Normally this is the easiest part of the question because the second derivative becomes very trivial, very simple. My second derivative here is going to be 8 minus 3x. Now that's my second derivative. That tells me where I'm concave up or concave down. I want to check that at the point that I found. So, I'm going to take this x and plug it in. I'm going to get 8 minus 3 times 16 over 3 times 3 divided by 3. Those are going to cancel out. 8 minus 16 is negative 8. So this is negative. This is concave down. This is a maximum. So sometimes you'll get a question that says prove that it's a maximum or a minimum, or sometimes you might not even know whether it's a maximum or a minimum logically. And so use your second derivative, find out if it's positive or negative at that point. Maybe worth pointing out for a second, if we do the same thing for 0, we get 8 minus 3 times 0, which is 8, which is positive minimum. Right? But anyways, that's not really what it is. So here's what we got. 16/3 is where we can find the maximum volume. Now, the very last thing about optimization, right, is that most of the time, when you find what you're looking for, you have not found the actual answer. If you walk into Google and you say 16/3, right? Is that the answer that they're actually looking for? No. We all found volumes that were way bigger than 16/3. 16/3 is not what they were asking for. So they might ask you for the dimensions of the box with the biggest volume, or they might ask you for the exact volume that is the biggest. So let's do that. Let's find the exact largest volume. So if we're going to find our exact largest volume, well, that would be volume equals 16/3 squared, right? I'm using the volume formula. Do you want to use the volume formula that was all in terms of x's? Or do you want to go over here and just figure out what the y was first and then put the y formula over there? What do you think? It's more or less the same thing, but sure, let's start with the y. So that would be 4 minus 1/2 times 16/3, which is going to be 4 minus 16/6, which can be simplified 16/6 to 8/3. And then we can maybe make 4 into 12/3 minus 8/3 is going to be equal to 4/3. And maybe I did that a little too fast. Maybe I wrote that a little too small, but whatever, you guys can do that. And so now, let's finish this question. The volume of my whole box would be 16 squared, 256, 3 squared, which is 9, 4 over 3, or not equals, times 4 over 3. Volume equals 1024 divided by 27. Now this number on the top is made up of entirely 2's, right? Because it's 16, which is made up of all 2's, and 4, which is made up of all 2's, and this bottom number 27 is made up of all 3's. So does this number reduce at all? No, they don't have any common prime factor. So this is the most simplified fraction answer. But at the end of the day, you know, maybe if you were at Google and they said, we're doing this question with no calculators at all, and in reality, maybe we want to write the volume as a number that would actually make sense to any normal person. So let's see Zach's calculator here. And let's see how we did as a class. 1024 divided by 27 equals, it looks like the maximum volume is 37.926. So, we've been doing this one question now for about 30 minutes. But all of this work aside, this little discovery that we did,
and if you don't have it, you're gonna be unhappy. Thank you.
That's great. All of this work that we did, which in reality, if we just kind of went right to the answer, wouldn't have been quite as long as 30 minutes. But anyways, the volume that we found as our peak absolute guaranteed highest volume is 37.926, which honestly, even as good as Sailor's was, we're getting 5 extra cubic inches for free, right? I mean, because we're not having to spend anything else on materials. We all use the same materials. And not only that, this is guaranteed the best, right? Google doesn't have to worry about another boy or girl coming around in a week and saying, I can improve your theorem. It's like, no. This is it. This is the guaranteed maximum. So finding these guaranteed maximums and minimums are super valuable. This also, in order to do that, 16/3 had to be the x value, which means 4/3 had to be the y value. If you are using a ruler, they don't really have thirds marked on the ruler. So even if you sat here and you tried every single notch on the ruler, you still never would have found a value this big, right? So all of those things just to say, this is valuable, relatively interesting, and also a little bit difficult, okay? Now, the biggest difficulty from this always comes from step 1, which is to actually make a function, okay? Optimization, the homework doesn't look like, make me a box with a volume of 10, make me a box, right? That's not how this works. The homeworks work with all different types of questions. Questions that have to do with area, questions that have to do with perimeter, questions that have to do with volume, questions that have to do with the length between 2 points. And it is always the most difficult step to make a function. And sometimes it's not very difficult, but it's always gonna be probably harder than taking a derivative because we're so good at that. Okay, we're done with this.